My turn? Hello everyone, how are we? Okay, so today, welcome to our talk today. Today is gonna be about astronomy in our daily lives. So it's mostly about appreciating astronomy as well as things that astronomy has brought us that we can actually observe all around us in our daily life, in our day-to-day. We might not realize it, but they're actually influenced by, in some form, by astronomy and by our knowledge in astronomy. So, well, let us begin then. So this is today's content roughly. We're going to be taking quick dives into a number of topics such as the length of the day, the days of the week, the calendar, the motion of the sun, how we can prove using very simple methods that the Earth really is round, as well as things that space exploration have brought us, some technology and gadgets, as well as the issue of light pollution that is so pertinent. Okay, so now let's begin with the length of a day. So how long is a day really? Now, we all know that a day is 24 hours long, but you probably also heard peripherally somewhere that a day is also 23 hours, 56 minutes, or 23 hours, 56 minutes, and 4 seconds long. So how long is the day really? Well, actually, the answer turns out that both are correct. Okay, 24 hours is actually the length of a solar day. That's how long the sun takes to return to the same spot in the sky. For example, from sunrise to sunrise, let's say it was for it to return to the eastern horizon, or sunset to sunset for it to return to the western horizon, or in the middle of the sky at noon, the time from noon to noon. So that is 24. That's the definition of 24 hours, the length of a day. Whereas 23 hours, 56 minutes, and 4 seconds, right? That's actually the length of a sidereal day, which is the time for the stars in the sky to return to the same place in the sky. In other words, that's how long the Earth physically actually takes to rotate one round, okay? And then it has to rotate a little more to face the sun again. It might sound a little confusing to some people right now, but okay, here's how it works, okay? This animation should help you to visualize, okay? But before I begin, okay, nothing in this animation right here is to scale, okay? In fact, it's very, very off scale. It's just to help you to visualize the idea of why there's a difference between a solar day, a synodic day, and a sidereal day, okay? So we have a model here, right? In the middle of the screen, we have a big yellow blob. That's our sun, okay? So we on Earth are at the little blue ball at the bottom. Okay, the bottom, that's Earth, that's us on Earth. And let's say we are on the red spot. Okay, Singapore is a little red dot. So, well, yeah. So we are on the little red dot. Okay, so right now it's noontime. Our side of the Earth is facing right at the sun. Right? Okay, okay. So now let us assume that the Earth starts off in this position. Okay, this is the start time of our model. And to rotate one round back to its current, for Earth to rotate one round back to its current position, right? Can we all agree that it is the amount of time it takes for Earth to rotate back to the top of the little blue circle, right? To the top, up, facing up, okay? Like you see here, okay? So here, now with these assumptions, okay, we also bear in mind that while the Earth is rotating, it is also revolving around the sun. Okay, both of these things are happening at the same time. And so with these, let's see what happens. Okay, so we go. So the Earth has rotated one round and also revolved some distance around the sun. Okay, again, this is not to scale, right? So now you can see that the Earth has rotated one round, right? It's facing up again. Okay, that's one round. But you realize that right now we're not actually facing the sun. So what? Then how? Which means that the Earth actually has to turn a bit more, okay, to face the sun again. So you realize that between this distance and this distance, actually, right, this extra bit of rotation takes time. And therefore, there is a difference in time between a solar day, which is the amount of time the sun takes to return to the same spot in the sky, and in other words, for us to be facing the sun again, and the amount of time it takes to just turn one round. In other words, well, a sidereal day is shorter than a solar day, a synodic day. And that's why, while of course this is very off scale, but the idea is that this is why a solar day is actually longer than a synodic day. Okay, there's actually a little mathematical mental shortcut to figure out the difference in time, right? So the idea is this: the Earth, right, it faces 300 degrees of sky. Okay, so we actually rotate once every 23 hours and 56 minutes and 4 seconds, right? So that is the amount of time it takes for the Earth to physically rotate one round. At the same time, we also revolve through the entire sky, travel around our orbit 360 degrees every 365 days, 365.256 days. So actually the shortcut is, if you take 23 hours and 56 minutes and 4 seconds divided by 365.256 256 days, okay, you actually get the difference between a synodic day and a sidereal day, which is about 3 minutes and 55 seconds something. Okay, so that's actually a mental shortcut for you. Yeah. Yeah, so this is the idea. And now, after we have talked about day, let's talk about week. Okay, we all know there are 7 days to a week. Okay, now what? But have you ever wondered, right? Why are the 7 days named like that? You know, Monday, Tuesday, Wednesday, blah blah blah, Saturday, Sunday. Okay, the reason is because it was named after the seven celestial objects, which we know, which people knew belonged in the solar system since ancient times. Okay, so these seven objects, well, the sun, the moon, these are the most obvious ones. You also have Mercury, Venus, Mars, Jupiter, and Saturn. 7 objects. Okay, we exclude Earth. Okay, we back then we thought we are the center of the universe, so ignore us, right? So in the sky there were 7 celestial objects. So each day is actually named after one of these celestial objects. The sequence of naming is based on how fast these people of the past ancient civilizations thought they moved through the sky, right? So we started with Monday because the moon, as you will see, Monday is named after the moon and so on. So all these names, right, we actually had to trace their roots all the way back to Old English, even the Germanic languages, the Nordic mythology, Roman mythology, and all that. But I'll explain later, okay, one by one. So, and you can actually observe this relationship in what is now Japanese. Okay, for those of you who know Japanese, think about how in Japanese, the days are actually written. Okay, and it's actually the same concept behind it. Okay, that happened because the same idea spread to the East, and the Chinese adopted it, which eventually spread to Japan, and the Japanese have kept it till this day. So, Monday. Okay, most of us hate Monday, right? First day of the week and everything. So Monday is named after the moon. You know, Moon Day, Monday. Well, well, somehow it became like this. Okay, so you can see it actually has its roots in Old English, and below you can actually also see the reference to modern Japanese. So for those of you who know Japanese, this you can also take a look at other planets, and you will figure out the reason why. Okay, yeah. So this is the moon, which is for Monday. Then we have Tuesday, which is after Mars, right? Because in Germanic mythology, Tu is the god which is equivalent to the Roman Mars, right? So Tuesday is essentially named after Mars. And then you have Wednesday. Wednesday is named Day of Woden, okay? And Woden is the equivalent of Mercury in Germanic mythology as well. Therefore, you can actually say that Wednesday is technically like Mercury's day and everything. Yep. Then you have the references to Japanese below. And then you have Thursday. Thursday, I believe a lot of us actually know the deity of Thor. Yep. So Thursday is Thor's day. I think we can all see the similarity here. Yeah. So and Thor is the Norse equivalent of Jupiter. Then we have Friday. Friday is named after the day of Friday, and that refers to Venus. And Saturday, well, Saturday is quite literally Saturn's day. And the N went somewhere, I don't know, but it's Saturn's day. Okay, yeah. And the easiest one, Sunday, the day of the sun. Sunday, yeah. There we have it. Yeah. What you see on the right, the picture is not the moon. It's actually a picture of the solar eclipse from 2019 that I took. Yeah. So Sunday. And now we talked about days, we talked about weeks. Now let's talk about the calendar as a whole. Okay, there are three main types of calendars in the world. Okay, the lunar calendar, which is based on the movement of the moon, the solar calendar based on the sun's movement in the sky, as well as the lunisolar calendar. So let's take a look at them one by one. Okay, now the sub points that you see are basically just examples of each of these calendars. So let's begin with the lunar calendar. One of the most commonly used one and the most well-known one is probably the Islamic calendar. So essentially, the Islamic calendar follows lunar phase cycles, which on 1 month on average, takes about 29.53 days. So the thing is that that is not how long it actually takes for the moon to go one round physically. Okay, that is how long it takes for the moon to go from new moon to new moon, which is the time it takes for the moon to go from between the Earth and the sun go one round and back to between the Earth and the Sun again. Okay, so it's the same idea as the synodic and sidereal day just now, just that now it's for the moon. So anyway, the lunar phase cycle is about 29.53 days. So because you have a 0.53 days, right? Let's just round it off to 0.5. Okay, there's the discrepancy. So how? That's why they actually divide each day to 29 days, each month to 29 days, a small month, or 30 days, big month. Okay, so therefore, each of your 12 months mostly lasts 354 days, sometimes lasting 355 days because you have extra fraction there to compensate for fractional differences. Yeah, and so you realize that each year actually Hari Raya Puasa or maybe or other Muslim festivals, right? They actually shift forward by 11 days each year. Okay, that's what happens. You can actually go and count, and really it's about on average 11 days apart most of the time. Okay, yeah. And then you have the solar calendar, which is what we're all familiar with now, the Gregorian calendar, which we all use right now. So it is based on the movement of the sun in the sky. In other words, the time it takes for the Earth to go one orbit around the sun, which is approximately 365.256 days. Okay, therefore, because you have the 0.25, roughly 0.25 days, so every 4 years it's a leap year, and you have the extra 0.006 days. Therefore, occasionally you actually every 100 years you have to remove a leap year. Okay, and sometimes you also have leap seconds. Leap seconds occasionally, there's an organization who will announce periodically to insert a leap second somewhere. So here and there you gain an extra second to compensate for the difference as well. And then you have the lunisolar calendar, which is the Chinese calendar, as we know. So it is a assortment of both the lunar calendar and the solar calendar. Okay, so you follow the lunar months, but you try to keep to a roughly the same solar year, because each year, right, each lunar year you are drifting forward by 11 days. But the thing is, the ancient Chinese, they were very agriculturally dependent on agriculture. So they had to check the seasons, right? Keep the calendar in check with the seasons, and therefore they came up with this lunisolar calendar to roughly keep the seasons in place. And because it's drifting forward all the time, you actually here and there you'll need the leap month to try to, as it drift forward, to put it back in place, and then it drifts forward again, then another leap month to put it back in place. So it happens every 2 to 3 years. Over 2,000 years ago, it was mathematically approximated. Okay, mathematically approximated that roughly you need 7 leap months every 19 years. Okay, that law has since been thrown out, but it's still a valid approximation. Okay, yeah, and that is also why that every year Chinese New Year seems to be on a different day, but somehow it always occurs between 20th January and 20th February on the Gregorian calendar, because it's roughly in the same place, but it's always drifting a little. Yeah. So now let us move on to the movements of the sun. Okay, not like this. Okay, this is the sun's rotation, but we're not going to be looking at the sun's rotation. Okay, instead we're going to be looking at how the sun is moving day to day. Okay, so the sun doesn't always rise from exactly east. Okay, it can vary depending on where on the planet you're situated and what time of the year it is. And as you can see on the right, that actually at different times of the year, the sun is actually rising from a different place. Yeah. So and here's an anecdotal incident which allowed me to realize to realize myself how actually the sun is actually rising at different points in the day. So that was my revelation. Okay, so essentially during secondary school, I believe most Singaporean students, we have a flag raising parade, right? So at the side of my parade square, there was actually this condominium. Okay, right at the due east, there was this condominium. So sometimes, right, the sun will be rising, and all of us will be like, oh, so bright, so hot, everything. Oh, the sun so strong. But on some days, the sun is comfortably behind the condominium, and then we don't feel anything until even after dismissal from site raising. So that was when I realized, hey, strange. The sun is rising from a different place every single day. So I went to find out, and that was when I realized, oh, so yes, the sun, I was like too, somewhat, that the sun doesn't always rise from the exact east. It varies from day to day. Okay, so let's go and take a look at a simulation. Here we are. Okay, here's a simulation, right? So I've set it to 0 degrees. That's where roughly, okay, so where Singapore is 1 degree, but I'm just gonna set it to 0, okay? And then every morning, so I'm gonna set it to 6:15. Okay, actually the sun rises in 7:15 and 7+ in Singapore, but by right it's supposed to 6:15. Okay, so Singapore is kind of in the slightly wrong time zone geographically. Okay, so now let's start the animation. Okay, and then you can observe, right? We have this guy in the middle. This, let's call him Billy. He's the observer here. Okay, and then you have the sun here. So the sun will move in its position every day, and let's try to visualize it. Yeah. So you can actually see that every day is moving moving north, then south, then north again. Okay, this is day by day, okay, with 60 days per second. So here you can actually see that the sun does rise from a different place each day. Okay, yeah. So you can see it in action right here. Okay, now, then moving on, I want to introduce to you this idea called solar analemma. Some of you might have seen it before, some of you haven't. It's essentially this figure of its shape that's in the sky. Okay, yeah. So if you took a picture of the sun every day at exactly the same time, let's say at 12 noon or any other time, I don't know, 10:52 or 4:19 or something like that, at the same time every single day, you will get some of a kind of a figure eight shape that you see here. Okay, so the vertical position, right, is actually due to tilt of the Earth. So the northernmost point here is actually the June solstice. The southernmost point is the December solstice. Okay, and then if you take this entire distance cut by half, you will have the equinoxes somewhere between. Okay, and then you might be wondering, why is there a figure of eight shape? Essentially, it's drifting forward eastwards and westwards because the Earth's orbit, if you remember from 2 weeks ago during the history of astronomy, right? Planets' orbits aren't exactly round. They are slightly ovalish, which is the eccentricity of an orbit. So the Earth orbit is also slightly ovalish, and that leads to slight variations between the length of day each year. Length of day each day, okay, over the course of the entire year. Sometimes it's closer to the sun, it will be moving faster. Sometimes it's further from the sun, it will be moving slower. And that has an effect on the length of a solar day throughout the year. Okay, and that will give you the solar analemma. So again, let's go there and try to see it in action. Okay, so here, right, let's set it to every day 12 noon. Okay, 12 noon. Okay, and then for the sake of visualizing, let's go to about 50 degrees. 50-degree latitude. That's about northern US, northern China, London, Paris, that kind of latitude. Okay, and then we will see the movement of the sun. Okay, you can actually see it tracing out the H shape if you observe every day. Okay, it's moving to the west, then back to the east and north again, and it kind of traces out an H shape. Yep, so that is the formation of an analemma. That's how it works. Okay, yep. Okay, moving on. Is the Earth really round, and how can we prove it? Okay, I'm just going to go through two very, very simple ways that we can all do. Okay, essentially, well, first way, gaze at the horizon. Yeah, essentially how the ancient Greeks realized the Earth was round. They first had this inkling was when they looked in the horizon at a boat sailing away, right? They realized that the boat itself will disappear from bottom up. Okay, the bottom of the boat will disappear below the horizon, and slowly it will sink below the horizon. That's how they realized. That's how they realized it. But the fact is that the existence of a horizon actually already indicates that the Earth is round because it has to be bending downwards. That's why the distance ground or sea is disappearing. That's how. And you realize that wherever you go, the horizon is there. So which means you have to keep bending, and by the time you bend back, you got a sphere, right? Yeah. So that's the idea. This is the simplest way to prove that the Earth is round. Another way is to observe the stars. Okay, I'm gonna use the northern celestial pole as an example here. Okay, so this is the star trails taken from somewhere near the equator. So you can see the northern celestial pole is all the way down here, just above the ground, right here. Okay, so anyway, this is an excellent photo, by the way, taken from this person. Yeah, so you can actually see a fireball right there. I think it's pretty amazing. So anyway, moving on. Now, if I move from the equator to somewhere at a high latitude or even the North Pole, I will realize the northern celestial pole, the center of the star trails here, is actually right overhead. So how does that work? Which means I have a sphere here. I must have a sphere here, okay? And then at the equator, I'm looking at the northern celestial pole, which is here, okay? I'm looking at it, is in front of me, just above the ground. Okay, but by the time I move to the North Pole, okay, I'm somewhere underneath. That's why the northern celestial pole is not overhead. So that means that the Earth has to be round. Okay, yeah. So these are just two very simple ways to prove it. There are a lot more actually. If you look at the solar analemma, right, you'll realize that at the equator, the analemma will be right overhead at noon, or it will be horizontally over the ground in the morning. Whereas in the North Pole, you'll realize, or the South Pole actually, you'll realize the analemma in the middle of the day is actually standing straight up. It's upright, an upright 8. Yeah. So that also happens because of the same reason as this, and proves that the Earth is round. Now let's go on to some byproducts of space exploration, essentially the technology that space exploration has brought us. Because you see, space exploration, it really is the pinnacle of human technology. It requires intense research and development efforts to get the top-notch technology. And a lot of it with that technology actually comes back to the general public for us to use. Okay, and it comes to daily lives in many ways that we may not realize at all. Some examples, okay, notable examples, the modern ballpoint pen. Okay, so the ballpoint pen was actually invented way before space exploration began, but the quality was poor and it smudged very easily. So in the 1960s, as astronomers started to have to go to space, right? So they had to find a way for astronomers to be able to write in space under microgravity or zero gravity. And at that point in time, pens didn't work because they needed gravity to pull down the ink to come onto the paper. So they had to invent something. So initially, what was thought was pencils, but pencils were found to be unfeasible because lead breaks, right? Pencil lead breaks, and the breakage of the lead, right? That little broken part can actually drift and eventually clog up circulation systems. And it had been demonstrated through experiments at that point in time that it can cause fire. So that was too much of a risk for them to take. So they had to come up with another way for the astronauts to write. So eventually, the modern ballpoint pen was involved, and that it was more viscous, and the ball was also smoother. So eventually, that made its way for the general folks to use. So now, if you have a ballpoint pen around you, right, you can try lying on a bed, lying down, and then writing. If you're lying down and you're writing against gravity, and your pen still works, right, that technology came from what was researched for the astronomers. Yep. Next example, improved shock absorption. Okay, improved shock absorption for buildings and structures. They were necessary for NASA to protect their launch pads from the huge force of launching rockets, and that was also protect spacecraft that were returning from space. So these technologies eventually made their ways to the general public and improved shock absorption technology for buildings, making them more earthquake and wind resistant. And some of these techniques are even incorporated into your cushions and mattresses to give you a better night's sleep, a more comfortable night's sleep. Yeah. Then you have miniaturized camera sensors. If you have a phone right now, well, you can take out your phone and take a selfie or anything. And that seems a very natural thing for us to do right now. But actually, the thing is, take a moment to appreciate how amazing it is that we can squeeze such a tiny camera sensor into your phone. And that actually came because of space exploration as well. Because in the late 1980s, right, engineers were trying to find a way for sensors to be made smaller but more efficient. Because originally sensors were big and they tended to be noisy. Okay, a lot of noise signals within them. So they had to invent something that was small but yet had a very good image quality. So in 1993, NASA engineer Eric Foster actually invented what is called the CMOS active pixel sensor, APS. Those of you who are into astrophotography might have heard of this before. Okay, so the CMOS APS was revolutionary and it would transform the entire photography industry. And thanks to them, with this technology, it could bring a form of photography to everyone. Now, in your phone, in your camera, laptop camera, which I'm looking at right now, yeah, or your GoPro if you have one, all of these utilize this same technology. Okay, all this same technology that came from space exploration allows us to take pictures everywhere we go. Yep. And lastly, the last section, we're going to be diving a little into the idea of light pollution. Okay, so light pollution, Singapore is one of the worst, the most light polluted countries in the world. It is measured empirically and proven that we are one of the most light polluted. Probably because, and some of the most light polluted cities are a lot of them are in Asia, probably because in Asia we believe that our cities have to be bigger and brighter and for it to look more prosperous. So everything that we build, we try to make the lighting more elegant, in some case exorbitant. Yeah. So yeah. So what is light pollution actually? The light pollution is actually the excessive and misdirected use of light at night, artificial light at night. Now the key word here is excessive and misdirected. Not saying that you cannot use light at all, but you can't use too much. You should not be using too much. Okay. Just for example, right, take a look at the picture on the left. Okay, this picture was taken at ECP last year when a few of my friends and I went for the conjunction. So you can see, right, you actually have a whole row of lights there. Okay, all of them are spaced less than 5 meters apart. And that's not all. Behind this row, right, you actually have another row and another row, all very close together and across the entire platform. So the light isn't just shining on the ground as well. The design of the light meant that it was scattering sideways and even upwards. So that begs the question, is it really necessary to make our night environment as bright as day? Well, I don't think so. So as amateur astronomers, right, our biggest complaint here is that light pollution drowns out the night sky. There are so many Singaporeans or urban dwellers who actually have never seen the Milky Way before, as well as many seen the Milky Way or any of the sky's hidden gems. Okay, but of course, right, this issue of light pollution goes way beyond what many call the wines of stargazers. Okay, well, it's not wine. Okay, the thing is, it has a lot of repercussions beyond astronomy alone. Okay, for example, you have disruption to natural ecosystems. Let's say for birds. Okay, birds rely on day and night cycles in order to maintain their sense of orientation and direction, and they also a lot of migratory birds also rely on starlight for navigation. Okay, yes, they do. They do celestial navigation. So when there's too much light pollution and too much artificial lighting, the birds are not able to maintain this sense of direction and orientation, and therefore, over time, they cannot migrate properly, or they are impacted by light pollution, and over the long term they die, right? Or let's say nocturnal species, a lot of them are not able to survive because we are in almost perpetual daylight because of these artificial lightings. Okay. Yeah, and there are many more species who are threatened by light pollution, and that can cause a serious imbalance to the region's ecosystem, even beyond the bounds of a city. Just let's say, for example, Singapore's light pollution dome, right, is actually visible nearly 100 kilometers away in Malaysia. Yeah, you can actually observe it and tell that it's Singapore's light dome. Yeah, and it's not just small animals that light pollution affects. Okay, it's also humans. Okay, we are one animal that light pollution affects without us realizing. Research has proven that exposure to a lot of unnatural light at night disrupts our circadian rhythm and also increases stress and boosts risk of psychiatric disorder and raises cancer rates and so on. That's because the body now has to work overtime, and now our circadian rhythm is disrupted, our hormones are imbalanced. So, well, is it worth all of these health risks? And last of all, energy wastage. Nearly a quarter of the world's energy consumption at night goes to lighting. Okay, you can imagine how much impact that has on the world's carbon footprint. Now, I don't think I need to elaborate on this point any further. Yeah. So that begs the question: how do we actually reduce light pollution? Okay. Now, the point is, we don't have to turn off all lights. Okay, we're not advocating for all lights to be turned off. That is irrational and excessive. We just need to learn to use our lights more efficiently. Okay, here are some examples. Okay, use light that point downwards appropriate coverings. One example you can see is actually on the left, the diagram on the lower left. Okay, you have different kinds of lighting. The most optimum one is this, the one on the rightmost of the diagram, where the light is actually shielded such that all the light is focused down on the ground. Okay, it's even better if the inner shielding is of a reflective material so that it can more effectively contain the light at the below the light itself, and make sure it is where it's supposed to be and not scattering everywhere like you see on the left side of the diagram, right? So this picture that you see above, right, is actually this condominium I came across, and this light, and I actually like the lighting a lot. I'm not sure whether you can tell, but the lighting is such that it's actually a rectangular box, right? And then on the top of the rectangular box, on the underside, right, that's where the light is. So it's shining downwards only, and it's not shining sidewards. And the top is actually iron, made of iron, so it's opaque. So all the light, as you can see from around here, right, is actually focused on the ground. Okay, the light doesn't scatter too far out. And if you see above and around it, it's actually still very dark. Yeah, so that is an example of efficient lighting. If we have more of such efficient lighting, right, not only are we reducing light pollution, we are also reducing a carbon footprint, because all of the lighting, all of the energy is now contained to be shining on the ground, which is where we want it to be. We want to see what's on the ground, we want to see the weight, right? So that's much more efficient. And it actually makes the ground much clearer and brighter also, while allowing the light to not allowing the light to scatter everywhere. Another way is to reduce the density of public lighting, such as in the case you saw just now at ECP. We don't actually need that many lights over there, right? We just need to have an amount that is sufficient and not excessive. Another way that's even more advanced, and I think it is a direction that we can work to as a smart nation, is to learn from Sweden. Okay, Sweden a few years ago they had this program where they installed street lights, right? That at night they will detect whether this road has a lot of cars passing through. When there are very little cars passing through at this time period, when there are no cars passing, no cars sensed, okay, the lights will actually dim down, or on some less populated, less traveled roads, they'll turn off altogether. And then when a car comes by and the sensor detects, then it will turn on the light. So that is actually a very ingenious way of using technology. And I think that is something that we can learn from, okay? And on a personal level, right, things that we can do ourselves is to turn off the lights when we don't need them, is to reduce your carbon footprint and also to reduce light pollution, and also to help improve your health, because too much lighting at night is really bad for you. Yeah. So these are some things that we can do to help reduce light pollution, maybe to improve our sky quality, and more importantly, to improve the society as general. And yeah, so that's roughly the end of the talk today. Here's the acknowledgement. Thanks to all these websites for the providing the pictures. And the rest of the pictures were mine. And yeah, that's the end. Thank you for coming, and I hope you enjoyed it and learned something from it. And follow NUS Astronomical Society or myself at the social media accounts below. And on this note, thank you for all your attention. I hope you have a great weekend ahead, and don't forget to keep looking up. You want to sit here and give the talk? Actually, you sit here.
Okay, hi everyone. I'm Ivy and I'll be doing the week 10 observation highlights. Woo! Okay. This is gonna be very basic, so don't expect too much. Okay, thanks. So what's cool happened recently is that on 20th March at 5:37 p.m. it was March Equinox 2021. So this marks the very first day of astronomical spring. So what's cool about March Equinox is that day and night are both of equal length and it's supposed to be 12 hours each, but in actuality, I think it was 12 hours and 6 minutes day and like 11. You do the math and you know what time, how long the night was. So yeah, that's what's cool about it. So yeah. So what's not so cool is that right now we're currently in waxing gibbous moon phase. So right now the moon is between a half and a full moon. What it's gonna mean it's gonna be much harder to stargaze as the moon is gonna cast a lot of light across our night sky, washing out many of our dimmer stars. But what's still cool is that it's going to be a great time to moon gaze, especially with a telescope or a pair of binoculars, because you get to see the craters and the seas of the moon. So this is a picture that I took a while back. So on the left is the waxing gibbous moon, and on the right is a full moon. So as you can see on the left, you can see much more craters and much more detail. And the moon on the left looks much more HD than the moon on the right. Yeah, the moon on the right looks much more washed out, but it is the full moon, so it looks pretty cool. So yeah. So this is my recommendation for tonight. It'll be the moon, Mars, Orion, M42, Canis Major, M41, M46, M47, and Tau Canis Majoris. Okay, and Orion, especially his belt, is a cool part. Okay, so right now you might not be wondering why did I group the last thing together, but you'll see why. Okay, so here's my tip for looking for the moon. Okay, so right, if you want to see the moon, all you need to do is look up, and you see a nice white round object with gray spots. It's most likely the moon. And if you see it, good job, because it's your first step to becoming a stargazing expert. Okay? Yes. And then you want to look for Mars, you want to look for a very bright star with orange tinge. So that's basically how you're going to look for Mars. I mean, there's not much else I can tell you other than that. Yeah. So for Orion, you want to spot his belt first. So that would be 3 stars in a straight line. Let's see the picture on the right, the picture I took of Orion, and you can see that the 3 stars is his belt. And you need to branch up from there, you get his torso and his legs. And then you can kind of see his dagger. Yeah, I mean, the screen is not very clear, but you can kind of see his dagger over there. So, yeah. And then M42 will be Orion's dagger. Yeah, it's a good picture that I have of the Orion Nebula. Yeah. So, if you look for Canis Major, it will be right around Orion, and you'll see a very bright star, which will be Sirius. So, that will be like the head neck-ish part of Canis Major. So, yeah, I think the picture is not very bright, but you can see a very bright star on the right, and that is Canis Major Sirius. Yes. So you like from that star you will go follow a trapezium, which will be Canis Major. Yeah. So for M41, M46, M47, and Tau Canis Majoris, right? You want to look for the extra cool people standing around the telescope. And all you need to do is ask nicely to see the aforementioned stars, and they will try their best to find it for you. Okay? So right, I don't have the skill to find these particular things, but those people around the telescope will be able to. So all you need to do is find someone with a telescope and then just ask them nicely, and then they'll find it for you. So that's my astronomy tip. Okay? So yeah, thank you, and I hope you have fun stargazing later. Yay! Okay. By the way, it'll be Earth hour tomorrow. 8:30 to 9:30, so that'll be a good time to stargaze also. But the moon will be out, right? So then it'll be off the lights tomorrow, okay? Okay. You help Wei Zhong out to stargaze.